The second chapter is simplex methods. Now allow me to recall the previous statements. To understand the following chapters, we mentioned before actually the common definition of operation research is to provide decision makers with tools and techniques to take an optimal decision. Optimal decision taking is depending upon the condition under which the decision is done. We listed 3 conditions when manager take a acceptable decision. Decision under certainty. Decisions under uncertainty. Decisions under risk. Decisions under conflict. عندنا الحالات التي يجب أن يعني الظروف circumstances التي يتخذ فيها قرار. المدير يتخذ قرار في حالة التأكد، في حالة عدم التأكد، في حالة الخطر، أو في حالة النزاع. But we will surround ourselves with 2 conditions for the purpose of our task: under certainty, under uncertainty. Under certainty shows that the information and the data are available. Therefore, we name this approach as a deterministic approach. The data are determined. Otherwise, as stochastic methods. The most suitable mathematical technique to apply the deterministic methods is linear programming. For deterministic methods, the most acceptable is the theory of probabilities. Now, we consider simplex methods as a branch of deterministic method, like the graphical method. So we base our progress in explaining and applying the simplex methods. On that fact, simplex methods belongs to deterministic method, where data and information are given. This is an essential entrance to understand what we are going to do. So I would like to emphasize that simplex method is the one of the deterministic model. The one of the deterministic model aims to solve the problem of maximization as well as minimization. Definition and scope. تعريف والإطار. The geometric methods of solving linear programming problem is presented before. It is not possible to obtain the graphical solution to linear programming problem of more than two decision variables or two products. What that means? Each graph contains of two axes, vertical one and horizontal one. Each axis represents one decision variable or one product, say x1. The other one represents other decision variable, for example x2. So the graphical method is valid in case the linear programming problems deals with two products, not more than two products. Otherwise, in case of more than two decision variables, the suitable method is known as the simplex method. It's the one of the most useful and efficient algorithms ever invented, and still the standard method employed on computers to solve optimization problem. So if you would like to distinguish between these two methods, one graphical method aims to solve the linear programming problem where consists, or if it consists of two decisions variable, x1 and x2, or two product only, while simplex methods can be used to solve LPP of more than two decision variables. Number 2, simplex methods is computerizable, is a computerizable model. We can apply computer programs instead of manual solution. So the two main differences between graphical and simplex method. Simplex method deals with more than two products, between brackets more than two decision variables, and it is computerizable, valid to be computerized. Simplex method is an approach for determining the optimal value of a linear program. The method produces an optimal solution to satisfy the given constraints and produce a maximum zeta value. Zeta means z belongs to the objective function. The main advantage of methods is that this type of computerized methods are more easy to handle compared to the graphical methods. But the common factor or the common share with these two methods, both of them deal with LPP that consists of its original components: objective function, constraints, and non-negativity condition. Non-negativity. As you know, this is a logical entrance to use both of these methods. Otherwise, we cannot apply either graphical or simplex methods. Summarizedly is said, the graphical approach can be used for two variable LP problem. Unfortunately, most real-life LP problems require a method to find optimal solution capable of dealing with several variables. The simplex algorithm is suitable to deal with more than two variable methods. I would like you to put these statements in account when dealing with the question of the differences between graphical and simplex methods. Simplex methods is a method to solve LPP models which contain two or more decision variables. The main terms of this model are basic variables. These are the variables which coefficients 1 in the equations and 0 in the other equations. Non-basic variables are the variables which coefficients are taking any of the values, whether positive, negative, or 0. Slack variable المتغيرات الهامشية. If the inequality be less or equal, then we add slack variable plus s to change the inequality from less or equal to equal, or actually from inequality to equation. طيب، عادة المتباينات أقل من أو يساوي تكون خاصة بمشاكل التعظيم. إذا كانت المتباينة أقل من أو يساوي نضيف S وهو عبارة عن المتغير الهامشي. في حالة المتباينة أكبر من أو يساوي وهي خاصة بمشكلة التدنئة نطرح المتغير الهامشي اللي هو ناقص S. إذن the function of slack variable is to convert inequality to equation. Easier to add S or to subtract it. We add S, slack variable, when the inequality is less or equal. We subtract S when the inequality is more or equal. The transformation with adding or subtracting S is known as a standard form. Standard form means to add S, to add slack variable, or to subtract slack variable negative S. Steps of application simplex methods. Step 1. Convert constraints to standard form. Make objective function zero equation. We clarified before that by adding or subtracting slack variable, we converted the constraints to equations or standard form. Number 2. Design the primal table by substituting the coefficients of variables. This primal table or essential table الخطوة الأولى هي تحويل القيود إلى معادلات بإضافة S في حالة إن القيد يكون أقل من أو يساوي، أو بطرح S في حالة القيد يكون أكبر من أو يساوي. القيد أقل من أو يساوي معناها نتحدث عن مشكلة بتاع التعظيم، أكبر من أو يساوي معناها نتحدث عن مشكلة تجميع التكاليف. طيب، ثم تحويل دالة الهدف إلى معادلة صفرية. Step 2 اللي هو to design the primal table. The primal table consists of the first row of the basic variables. الصف الأول في هذا الجدول the upper row جدول الصف الأعلى represents the basic variables المتغيرات الأساسية. The first column to the left represents non-basic variable. Our target to move the decision variable from the non-basic row to the basic column of variables. The contents of the cells of the table consist of the coefficients of variables. For example, the first constraint is 2x1 plus 3x2 plus s1 equal 40. That means 2 is the coefficient of x1, 3 is the coefficient of x2, and 1 is the coefficient of s1, and the solution equal 40. Later on it will be easy to understand. Step 4, select entering and exiting leaving variables. نحدد المتغير الداخل والمتغير الخارج. Find the pivot element اللي هو العنصر الأساسي the main element. Determine the main equation معادلة المحور عنصر المحور. Apply the process of leaving and entering values. Iterate the solution up to disappearance of the negative values in objective function or zeta function. Prove the solution. طيب, where the end of the solution? When we capture the optimal solution. متى نصل إلى الحل الأمثل؟ حل مشاكل السمبلكس يقوم على التحديث iteration إلى أن نصل إلى حالة اختفاء القيمة السالبة في دالة الهدف. عندما تختفي القيمة السالبة في دالة الهدف نكون وصلنا إلى الحل الأمثل. we reach the solution, the optimal solution, when the negative value in the objective function are disappear. عندما تختفي القيم السالبة في دالة الهدف، حينها نكون وصلنا إلى الحل الأمثل. في حالة التنمية عندما تختفي القيم الموجبة. In case minimization, we reach the optimal solution in case of minimization when the positive value are disappear. The difference between two methods. Now let's see how to apply these steps practically. The simplex method consists of having a trivial basic feasible solution to the constraints equation, testing whether it is an optimal solution or not, improving if required the first real solution by a set of rules, and repeating the process till an optimal solution is obtained. LPP is said to be standards maximization problem in standard form if its mathematical model is of the following form: Z equals C1x1 plus C2x2 plus Cn xn. It is an objective function subject to problem constraints of the forms a1x1 plus a2x2 plus anxn less or equal b. B is more or equal 0, most time is more than 0, stands for resources available, with non-negativity condition that x1, x2 and xn more or equal 0. This is the required contents to apply the simplex methods. Slack variable, as mentioned, represents the unused resources ويعبر عن الموارد أو المواد التي لم يتم استغلالها. When the constraint is less or equal, slack variable should be added, otherwise should be subtracted. For example, given the following linear programming problem where max z equal 4x1 plus 10x2 subject to 2x1 plus x2 less than 50, 2x1 plus 5x2 less than 100, 2x1 plus 3x2 less than or equal 90, x1 x2 more or equal 0. Right. Now الو 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 فايز، كيفك؟ اخبارك؟ Now the first step to convert inequalities constraint to standard form. Once inequality is less or equal, then we are going to add s1. 2x1 plus x2 plus s1 equal 50. 2x1 plus 5x2 plus S2 equal 100. The last constraint 2x1 plus 3x2 plus S3 equal 90. Notice that the slack variable for constraint number 1 is S1. The slack variable for constraint number 2 is S2. The slack variable for constraint number 3 is S3. That's why. So S1 represents first constraint, S2 represents second constraint, S3 is for the third constraint. يا فايز ما بسمعك يا اخوان.
من وين هو؟
السودان بكم. Okay. So here we converted the objective function to zero equation. Z minus 4x1 minus 10x2 equal 0. It was Z equal 4x1 plus 10x2. So we pushed the 4x1 and 10x2 to the left side, and we got Z minus 4x1 minus 10x2 equals 0. This is a zero equation. Now the contents of the primal table. Check the first row. The upper row consists of x1, x2, s1, s2, s3 and solution. The values inside these cells represent the coefficients of variables. Now if we return back to the standard form, 2, it is a coefficient of x1 in the first constraint or in the first standard form or equation. 1 is the coefficient of x2. The next one is the coefficient of s1. In the first constraint there is no s2, respectively there is no s3, then their coefficients is 0, 0. The solution is the resources B in case of the first constraint. طيب S1 يعبر عن القيد الأول. إذا رجعنا إلى الستاندرد فورم، القيد الأول هو عبارة عن 2x1 plus x2 plus s1 equal 50. إذن 2 هي معامل x1 و x2 المعامل بتاعها 1 و s1 المعامل بتاعها 1، وليس لدينا s2 و s3، لذلك المعاملات ل s1 و ل s3 هي 0 0. 50 هي عبارة عن الموارد. S2 تعبر عن القيد الثاني. في القيد الثاني معامل x1 2، معامل x2 5، ليس لدينا s1 في القيد الثاني ولذلك المعادل 0. هنالك s2 في القيد الأول المعامل بتاعها 1، وليس لدينا s3 في القيد الثاني ولذلك المعامل 0. السوليوشن هو عبارة عن 100 وهي الموارد المتاحة للقيد الثاني. القيد الثالث عبرنا عنه بالمعادلة 2x1 plus 3x2 plus s3 equal 90. اثنين هو معامل x1 في القيد الثالث 3 هي معامل x2 لا يوجد لدينا في القيد الثالث s1 و s2 ولذلك معاملاتها هي 0 0. s3 في القيد الثالث هو معاملها 1. الموارد المتاحة للقيد الثالث هي 90. Now the first check the second row which stands for S1. Where is 2 is coefficient of x1, 1 is the coefficient of x2, s1 is the coefficient of s1. In the first constraint we have no s2 and f3, then their coefficient are 0 0. The solution is 50. Move to the second constraint. S2 represents the second constraint where the coefficient of x1 is 2, the coefficient of x2 is 5, no s1 equals 0, the coefficient s2 equal 1, s3 equal 0, the solution is 100. S3 represents the third constraint where 2 is the coefficient of x1, 3 is the coefficient of x2, 0 0 and 1 the coefficient of s3. The available resources equal 90. Z, the first is negative 4 and negative 10. There is no s2, s1, s3 solution, therefore equal 0. Refer to the primal table. Please copy the table and follow the steps. رجاء انقل الجدول لكي نسهل عليكم عملية فهم الحل. Please copy the table and follow the steps to simplify the process of solution. Step 4. We need to determine the entering value. المفروض ندخل هو مش we need to determine the entering variable, not value. The definition of entering variable is that variable which faces the biggest negative value in the row of Z. ما هو المتغير الداخلي؟ entering variable. entering variable متغير الداخل هو المتغير الذي يناظر أكبر قيمة سالبة في دالة الهدف. Return back to the primal table. We found that the biggest negative value in the last row or the row of Z, we found the biggest negative value is negative 10. And the variable which faces this negative 10 is x2. Notice please, x2 is placed in the upper row. This x2 faces negative 10 in the lower row. Then we call x2 is entering variable, متغير الداخل. الذي يناظر أكبر قيمة في دالة الهدف. المتغير الداخل هو نجده في الصف الأول أو الصف الأعلى non basic variable، في صف non basic variables. هو المتغير الداخل أو x2 should be converted transform from non-basic to basic variable. So it will substitute leaving variable. We mentioned before that the first left column consists of basic variable. The first upper row consists of non-basic variable. We need to convert x1, x2 from non-basic to basic variable. So, to replace easier s1 or s2 or s3. So now x1 should replace easier s1 or s2 or s3 to replace the leaving variable اللي هو المتغير الخارجي. Now how to determine the leaving variable? Let's use the calculation. Check the right column of solution and check the column under x2. We are going to divide the column of solution over the column under x2, except the negative and zero values. Except the negative and zero values. Now, we found 50 over 2, 100 over 5, and 90 over 3, respectively equal 50, 20, and 30. The least value is 20. We found 20 by division 100 over 5. 100 over 5 is calculated. The result of calculation in the third in the row of S2. Then S2 is said to be leaving variable, said to be leaving متغير خارجي. كيف نحدد المتغير الخارجي؟ ننظر إلى عمود الحل وهو العمود الأخير على اليد اليمين. نقوم بقسمة كل القيم الموجودة في هذا العمود على ما يناظرها من القيم الموجودة تحت أو في عمود المتغير الداخلي وهو عمود x2. إذن سوف نقوم بقسمة 50 على 1، 100 على 50 على 5، و90 على 3. أقل قيمة من حاصل هذه القسمة هي 20، وهي عملية حدثت في صف S2 أو الصف الثالث، ولذلك نعتبر S2 متغير خارج ليحل محله X2. ثم then we are going to determine the pivot element أو العنصر المحوري. The pivot element is the intersection cell، خلية or value between the entering and leaving variable هي القيمة التي تقع في نقطة التقاطع بين المتغير الداخل والمتغير الخارج، إذن بين x2 و s2 وهي تساوي 5 إذا عدنا إلى البرايمال table. Pivot element is intersection value or cell between the entering and leaving variable, then equal 5. Step number 7 is to find the pivot equation. The pivot equation is exiting row or leaving row over pivot element. Then leaving row over pivot equation. Exiting row or leaving row is the row of S2 2 5 1 0 0 100 over 5 pivot element. The result is 0.4 1 0.2 00 20. This is known as pivot equation, or the values of x2 in the next table replacing s2. يعني s2 will be kicked out. Instead of s2 we will replace x2. بدلا عن s2 هتكون عندنا x2. Now x2 is moved from non-basic variable to basic variable. We pushed, transformed, converted x2 from non-basic to basic variable. S2 gone out of our optimal solution. Okay, the entering of x2 as basic variable will lead to change in S1, S3 and Z, resulting from the entering of x2 as basic variable. How S1 will change? Check the following table to determine the new S1. Why new S1? The new S1 is the resulting from the entering of x2 as basic variable. The first row copied the values of S1 as given in the primal table. Let's check the pivot element of S1. The pivot element of S1 equal 1. Intersection point or intersection between S1 and X2 as entering value. العنصر المحوري ل S1 هو ذلك العنصر الذي يتقاطع مع عمود x2, which is determined as entering variable. Now, this pivot element should be multiplied by pivot equation, which also is determined before. The results are 0.4, 1, 0.2, 00, 20. This is the result of multiplication of pivot element of S1 times pivot equation, and we subtract 0.4 from 2, 1 from 1, 0.2 from 1, etc. New S1 is 1.6, not 1.8, and 1, 1, 0, 1.8, 0, 0, 50, negative 20 is 30. This is a new, how to find the new S1. How to find the new S1. The same scenario, how to check the change in S3 resulting from the entering of x2 as basic variable. We are going to copy S3 as given in the primal table. The second operation represents by the second row pivot element of S3 multiplied by pivot element which is given. This is the result of multiplication: 1.2, 3, 0.6, 00, 60, and new S2 is 2, negative 1.2 is 0.8, 3 minus 3 is 0, 0, negative 0.6 is negative 0.6, 0 minus 0, 0, 1 minus 0, 1, 90 minus 60 is 30. This is a new S3, the new S3, and this is the impacts of S3 by the entering of x2 as basic variable. As you see, we just repeat the same steps in determining the effects of new basic variable. Last step also we will repeat the same instructions in determining the new z as a result of the entering new basic variable x2. Copy z as given in the primal table: negative 4, negative 10, remain 0. Pivot element of z multiplied by pivot equation. The harvest is negative 4, negative 10, negative 2, 00, 100. So we will get the table below. As you see, there is no all the values are positive. There is no negative values in Z row, where S1 is 30, X2 is 20, S3 is 30, Z is 200. There is no X1, that means X1 equals 0. There is no S2, that means S2 equals 0. So this table shows that S1 equal S3 equal 30, S2 equal 0, X1 x equal 0, X2 equal 20, and Z equal 200. Now example 2, please again copy the givens and table to follow the instruction and steps of solution. Max Z objective function equal x1 plus 3x2 subject to x1 less than 5, x1 plus 2, x2 less than or equal 10, x2 less or equal 4. The non-negativity condition, of course, x1, x2 more or equal 0. We are looking to solve this using simplex methods. The first step is to convert the constraint to the standard form. So the first constraint will be x1 plus s1 equal 5. The second constraint will be x1 plus 2, x2 plus s2 equal 10. The last constraint will be x2 plus s3 equal 4. Z0 or objective function should be 0 equation. Then z minus x1 minus 3x2 equals 0. Design the primal table by inserting the coefficients of all variables. As you look, the first row, upper row, consists of non-negative, non-basic variables. The second stands for S1. The third stands for S2. The fourth stands for S3. And the last stands for Z or objective function. The row number 1 or the row S of S1 consists of the coefficients of x1, x2, s1, s2, s3 and solution in the first constraint. Return back to the first constraint where the coefficient of x1 is 1, there is no x2, then the coefficient equals 0. There is s1, the coefficient is 1. There is no s2, s3 respectively equals 0, 0. The solution is 5. The second constraint is x1 plus 2, x2 plus s2 equal 10. So the values of s2 is 1, 2, 0, 1, 1 and 10 as solution. S3 consists of x2 and s3 and solution only. Here there is no x1, there is no s1, there is no s3, s2. So the contents of this row is 0, 1, 0, 1, 4. Z equal negative 1, negative 3. The remains are 0. Please again copy these givens and copy the primal table in order to follow our instruction and steps in the process of solution. Otherwise it will be so difficult to understand the solution of this problem. Based on the above mentioned rules, entering variable x2, leaving variable s3, pivot element 1. Pivot equation is 0 1 0 0 1 4, and the values of x n in the next table. Now just follow the impacts of entering x2 as basic variable on s1, s2 and z. The result of calculation gives that the new s1 is 1 1 1 0 1 0 0 5. The new s2 is 1 0 0 1 negative 2 2, and the new z is negative 1 0 0 0 3 and 12. The last new z shows that we need to design next table, because still we have negative value here. We mentioned before, we reach the optimal solution when the negative value in the row of z will disappear. So we need to design table to avoid the negative values. That we are going to do. The second table is given as, let's check that x2 replaced s3, x1 is new entering variable, s2 is leaving variable, the pivot is 1, pivot element is 1, pivot equation is 1 0 0 1 negative 2 1, and this will be the values of x1 in the next table. So how we determine x1 as entering value? Because it faces the negative value in the row of z, which is negative 1. Only one negative value. Okay, and we determined s2 as leaving variable because 5 over 1 is 5, 1 over 1 is 1, the result is 1, then s2 is leaving. So as you see, s1 will stay as valid variable, s2 and s3 will equal 0 in the last version. We will get s1, x1, x2 and z. The entering of x1 as a basic variable will impact on s1, x2 and z. The new s1 will be 0 0 1 negative 1 2 3. The new x2 will be 0 1 0 0 and 4. The new Z will be 000, 11 and 14. 11 and 14. Now we are going to design the last table. We are going to design the last table. Okay, pay attention to the table number 3. We reached optimal solution because there is no negative values in the row of Z. But let us read the values of this table. S1 equals 3. Check the last column on the right side, the column of solution. S1 equals 3. There is no S2 and no S3. That means S2 and S3 equal 0. X1 equal 2. X2 equal 4. Z equal 14. Let's prove our findings. Now, if refer to standard form, x1 plus s1 equal 5, x1 equal 2, s1 equal 3, it is 5, proved. The next constraint, x1 plus 2, x2 plus s2 equal 10. There is no s2 equal 0. x1 equal 2, x2 equal 4. 2 times 4 equal 8. 10, proved. x1 plus s3 equal 4. 4 plus 0 equal 4, proved. Z equal x1 plus 3x2. Z equal 2 plus 3 times 4 equal 14. Then, to maximize profit, firms should produce 2 units of x1 and 4 units of x2. The optimal solution within given constraints. This, please recheck these 2 problems. If any questions, reply please using the various social media. Okay, example 3. Solve the following LPP, linear programming problem, by using simplex methods. Given the objective function max z equals 6x1 plus 4x2. So this problem deals with 2 decision variables and x1 and x2, and the parameter for x1 is 6, which indicates the profit of 1 unit of x1, and for the parameter of x2 denotes the profit of 1 unit of x2, subject to the constraints x1 plus 2x2 less than 720, 2x1 plus x2 less than or equal 780, and the last constraint is x1 less than 320, the non-negativity condition x1 x2 more or equal 0. So let's move. As we experienced before, let's follow the mentioned below the steps. Step 1, convert the constraints into the standard form. Standard form means add or subtract slack variable s. So the constraints will take the following shapes: x1 plus 2x2 plus s1 equals 720, 2x1 plus x2 plus s2 equals 780, and the last constraint is x1 plus s3 equal 320. This is the first step, as we emphasized before, to convert the constraints or inequalities into the standard form. Step 2, to convert objective function into zero equation. So we are going to move the two decision variables to the left side, and we will get z negative 6x1 negative 4x2 equal 0. So the next step is to design the primal table. Or essential table, or table number 1. First step, convert the constraints or inequalities to the standard form by adding s or slack variable. The second step is to convert objective function into zero function by moving the right side to the left side, and then we will get zero function. Okay, this is what you call it primal table or essential table or table number 1, referring to the standard form of constraints. So this table will be designed. So the first upper row consists of the basic variable or non-basic variable, which now is are x1, x2, s1, s2, s3, and solution. The status of mentioned variables now is non-basic variable. Our target is to remove x1, this non-basic variable, from the condition of non-basic to the condition of basic variable, instead of S1, S2 and S3. Now, before the process of solution or the iteration, the left column consists of 3 variables which are known now as basic variable. No? So our objective is to remove non-basic variables to the basic variable, replaced S1, S2 and S3. To implement this target, step 1 or step 4 now, to determine the entering variable. Entering variable defined as that variable which faces the biggest negative value in the row of the objective function, or Z row. So the biggest negative value as shown is, here we have two negative values. X1 faces -6, X2 faces -4. So X1 should be considered as entering variable because it faces -6, which is the biggest negative value in the last row of Z. So step 5 is to find or to determine exiting variable. Now, as we mentioned before, by division, the column of solution by the column of x1 except negative and 0 values, the exiting variable is S3. Now let's check. (720 over 1 equals 720). (780 over 2 780 over 2 is more, of course, than 320. Is more than 320. Actually, 780 over 2 is 390. 390. So the result of this division is 720, 390, and the last division is 320 over 1 equals to 320. Now S3 is considered as exiting variable. The pivot element is the intersection point between the row of exiting variable and the column of entering variable, which is 1. The pivot equation S3 existing variable or pivot element 1 trivial 0 1 320 over 1. Okay, so the value of x1 in the next table instead of s2 is 1 trivial 0 1 320. So now this is the main equation. We will use it later to calculate the change in other basic variables like S2, S3 and also Z. Now we will depend on the pivot equation to continue our solution. Now focus on this pivot element. Also it is the values of x1 in the next table. Let's continue. Reformulation of new table based on the entering or entrance of x1 as new basic variable. The entrance of the x as new basic variable will lead to the change in S1, S2 and Z. In this case, we will follow the following rules. First, we have to determine the pivot elements of S1, S2 and Z. The pivot element of S1 and S2 and Z is the intersection point between the rows of S1, S2 and Z and the entering variable, which is x1. Okay, these pivot elements of this variable should be multiplied by the pivot equation and subtracted from the original values of S1, S2, S3. Okay. Looking at the primal table, the values of S1 are 1, 2, 1, 00, 720. The result of multiplication of the pivot element of S1 by the pivot equation equal 1, 0, 0, 0, 1, 320. By subtraction, these values from the original values of S1, we will get new S1. 1, 2, 1, 0, negative 1, 400. This is the values of S1 in the next table. The same sequences will be used for S2 and for Z. Just repeat the same procedure. The process of reformulation of the non-basic variables S1, S2 and Z, we will get table 2, secondary table. This of course is a process of iteration of solution. So the new table consists of three basic variable. Now x1 is the new basic variable instead of s3. Now let's repeat the same steps in order to find or to determine the new entering variable and the new exiting variable. Using the same tools, now x2 is entering variable and s1 will get out is exiting variable. The element is 2, intersection point between the column of x2 and the row of s1. The pivot equation is the result of division of s1 over 2. S1 over 2 will get a pivot element and also the values of x2 in the table number 3. As we mentioned before, x2 is entering variable while s2 is exiting variable and pivot element equal 2. Accordingly, pivot equation equal s2 over 1. What do you mean by the variable s2 over 1? So s1 s2 over 1 equal 1 0 1 0 1 negative 2 and 140. So now this is a pivot equation as well as the value of x2 in the next table. Reformulation of variable based on the appearance of x2 as basic variable. The change will occur s2, x1 and z. The impact of entrance of x2 as basic variable on s2, x1 and z. Let us see in the next slide which changes will occur. Okay, by repeating the mentioned procedure of measuring the entrance of new variables as basic variable, we will get the new S1 equal 0 0 0 negative 2 3 120, the new X1 as it is 1 triple 0 1 320, and new Z is 0 0 0 4 negative 2 2480. Let's move to the third table and to see if the iteration of solution is a start. Okay, this is table 3. It seems the last table of iteration. Now just focus on the values of Z. 0 0 0 4 negative 2. The rule states that the iteration of solution and the optimal solution will be captured when the negative values in Z row will disappear or disappeared. Now, as you see, the function Z has no negative values. Mainly we mean by the negative values that values which faces the basic variable x1 x2 actually, not which faces s1 s2 and s3. As we mentioned before, s1 s2 s3 as slack variable, because we designed these variables to process the solution of simplex method. They are not an original variable. We created this variable. So look to the table as a whole and see the value of S1 equal 120. Focus on the last or look at the last column of solution. X2 equal 140, X1 equal 320, and Z equal 2480. So, but this is not the last station. Now we have to look after the proof of these findings, the application of these findings to what? To the objective function and to the constraints in order to correct them. Okay, proof. Given x1 equal 320, x2 equal 140, s1 equal 120, s2 equal S3 equals 0 and Z equal 2480. Check constraint number 1 where x1 plus 2x2 plus s1 equal 720. Now this 720 equal actually 320 plus 2 times 140, 2 times 140 because x2 equal 140 plus 120 because s1 equal 120. The addition of this operation, the result of this operation equal 720. Proved. Let's move to constraint number 2. State that 2x1 plus x2 plus s2 equal 780. Then 2 times 320 because x1 equal 320 plus 140, x2 equal 140, s2 equal 0. So the result is what? 780. Constraint number 3 states that x1 plus s3 equal 320, s3 equal 0. Then 320 plus 0 equal 320. Proved. Let's check the objective function z. Objective function equal 6x1 plus 4x2. 6 times 320 plus 4 times 140 equals 2480. Check table 3. Thank you. So just look at this proof through table number 3.